Every major automaker on Earth is chasing the same number. Not horsepower, not top speed. A single figure buried in spec sheets that determines whether an electric car company survives the next decade: energy density per dollar. And right now, one company is quietly winning that race by a margin most people don't understand. It's not because Tesla invented a new kind of battery. It's because Tesla stopped thinking about batteries as a part they buy and started treating them as a system they designed from the atom up. This is the real story of how Tesla pulled ahead and why the lead might not last forever. Here's what should confuse you. Tesla doesn't manufacture most of its own battery cells. Panasonic, LG, and CATL still make the physical cells that power a huge share of Tesla's fleet. So if Tesla isn't even building the cells, how is it beating companies that build nothing but batteries? The answer isn't in the chemistry lab. It's in 3 decisions Tesla made over a decade ago that almost nobody else was willing to make. Decisions about how cells are shaped, how they're packed together, and how they're allowed to fail. By the end of this video, you'll understand exactly why a Tesla battery pack can pack in more range per kilogram than most competitors, and why that advantage is now closing faster than Tesla would like. Before we get into the engineering, there's one specific design choice Tesla made in 2020 that its competitors still haven't fully copied. A change so unglamorous that most reviewers ignored it, but one battery engineers consider one of the most important structural shifts in EV history. We'll break that down at the 8-minute mark, along with the one weakness in Tesla's approach that's already letting rivals catch up. Stick around, because that weakness is the whole second half of this story. The cell shape nobody else wanted. Most EV makers in the 2010s used large pouch or prismatic cells, big, flat, rectangular batteries that are easier to manufacture in bulk. Tesla went the opposite direction. It leaned into thousands of small cylindrical cells, originally borrowed from laptop battery form factors, and packed them by the thousands into a single pack. On paper, that sounds inefficient. More cells means more connections, more potential failure points, more complexity in manufacturing. So why do it? Because small cylindrical cells solve a problem almost no other automaker was willing to engineer around: thermal management at scale. When one cell in a massive pack overheats, a design with thousands of small cells can isolate that failure to a tiny fraction of total capacity. A design with a handful of huge pouch cells can lose a much larger chunk of the pack, or worse, propagate a thermal event to neighboring cells. Tesla essentially bet that manufacturing complexity was solvable with automation, while thermal safety at scale was not solvable without a fundamentally different cell architecture. That bet paid off, and it's a big part of why Tesla battery packs have historically had lower fire incident rates per mile driven than several competitors using larger format cells. The structural battery pack. Here's where Tesla's engineering gets genuinely unusual. In a traditional EV, the battery pack is a separate, heavy component bolted underneath a car body that was largely designed the same way a gasoline car would be. Tesla's newer platforms, starting with the Model Y built at its Texas and Berlin plants, do something different. The battery pack itself is part of the car's structure. The pack isn't just carrying energy, it's carrying structural load, the way a wing spar carries load in an aircraft. This matters for one simple reason: weight. Every kilogram of dedicated structural framework that a structural battery pack eliminates is a kilogram that doesn't need to be hauled around for the entire life of the vehicle, which means more of the car's total weight budget can go towards cells instead of scaffolding. Fewer structural components, fewer manufacturing steps, and a lighter overall vehicle for the same range. It's an approach borrowed conceptually from aerospace composite design, where the skin of the aircraft carries load instead of just covering an internal frame. Software nobody else fully matches. This is the part almost no competitor advertises, because it's invisible. Every Tesla battery pack is managed by a battery management system that doesn't just monitor charge level. It individually models the health, temperature, and degradation curve of clusters of cells in real time, using data pulled from Tesla's entire fleet. Tesla has been collecting real-world battery degradation data from millions of vehicles for over a decade. That dataset lets Tesla software make decisions competitors can't easily replicate. Precisely how fast to charge a pack without accelerating degradation, precisely when to balance cell groups, and precisely how to extend usable range as a pack ages. A battery is not just a chemical device. It's a system that behaves differently depending on how it's charged, how it's cooled, and how it's discharged over years of use. Tesla's edge isn't only in the hardware. It's in a decade of fleet data-feeding software decisions that squeeze more usable life out of the exact same cells a competitor might be using. Let's pull this apart into what actually matters. Insight 1. Tesla's advantage was never really about inventing better battery chemistry. It's about system-level engineering, cell shape, pack structure, and thermal management working together as one design, rather than a battery pack treated as a separate component bolted onto a car. Insight 2. The structural battery pack, introduced in 2020, is the change we teased earlier, and it's genuinely difficult for legacy automakers to copy, because it requires redesigning the entire vehicle platform around the battery, not just swapping in a new pack. Most competitors are still retrofitting battery packs into body designs that weren't built for them. Insight 3, and the weakness we promised. This lead is narrowing. Chinese manufacturers, particularly CATL and BYD, have pushed hard into similarly integrated cell-to-pack and cell-to-chassis designs, skipping the module step entirely and building packs that are structurally and thermally competitive with Tesla's approach, often at a lower cost per kilowatt-hour. Tesla's manufacturing lead bought its several years of runway. That runway is shrinking fast. So the real question isn't whether Tesla currently has the best battery engineering on the road. Right now, by most independent range per dollar and thermal safety metrics, it does. The real question is whether system-level engineering advantages like this one can survive once every competitor learns to copy the playbook. If you want to see exactly how China's battery makers are closing that gap, and which one might actually be ahead already, that's the next video, and it's a very different story. Subscribe if you want to see it the moment it's out, and drop a comment. Which automaker do you think closes the gap first?